Learn key concepts for keeping API servers secure, from cores to error handling to rate limiting and more. Anthony Aragues from APIsec Labs created this course. He has worked in security for over 20 years.
Hi, I'm Anthony Aragues, and this is the Securing API Servers course by APIsec University. I'll be your host throughout the course, telling you some ways to better secure your API servers from what we've seen in the field. This course could be for you if you are in or interested in development, operations, security, or any combination of those three. The course is broken up into 6 sections. Each one we go into as much detail as possible with scenarios and why you need to care. These are chosen based on how often we see them and how well they're understood and how much value you can get out of paying attention to these specific security configurations. So if it sounds like a course that might be for you, you can get some information out of it that can help you secure your API server, then let's go ahead and get started. We've got 6 different ones. You don't have to do them in any specific order. And we do have a certificate at the end if you want to display it on your LinkedIn page or resume. See you online. Hi, I'm Anthony Aragues for APIsec Labs. In this video, we will cover CORS, also known as cross-origin resource sharing. It's one of the most common vulnerabilities we find and not often well understood. CORS is just a set of suggestions for how browsers are allowed to serve content. Those suggestions come from where the content is provided. It's on your API server that's going to say how people are allowed to use that content, and it's the browsers that have to respect it. CORS will define what is allowed to be called from where. So the what can be endpoints and methods, things like post and get, and things of that nature, and where it can be called from. So your UI that is intended to call an API is going to be allowed by that API. But then if somebody else tries to point to your API because you don't know them, you can block that because it's not on the allowed list. And you can do that for individual endpoints. And some endpoints you might allow very free and open access to, as long as you know that that's not going to be protected or it can be misused. CORS is a pretty basic security configuration for a web server. It can feel like it gets in the way sometimes, especially when you're doing development. Your local host is not allowed to communicate with an API. Like you're developing a new UI and you want to communicate with the production API, which is a pretty common scenario. If that production API doesn't allow you to use it from localhost, then you're going to get these CORS errors and just feel like it's in the way. Those restrictions are good for when you don't want people to impersonate you. You don't want people to use your branding or your intellectual property, or for them to set up different scenarios where unsuspecting users think that they are going to your site, but they're going to a different one using the data for your site and your API through theirs. And CORS can help you protect against this stuff. What's key to understand is that CORS is not going to protect you from direct attacks. I drew up this quick little diagram to show you that if a malicious system is going to talk directly to your API, it can ignore CORS because CORS sits in the browser and it sends signals to the browser and the browser has to respect it. So if somebody's directly attacking your API, they're not going to respect anything that it says that you can or can't do with their content. It's only the browsers that are going to respect this at all. And that's why this is specifically for the scenarios of your unsuspecting users going to a malicious site or a mixed use site and using your API or your content in a way that you wouldn't normally approve of. So how do we get into the situation? I kind of alluded to it before, but I've been in this situation many times where you're creating something new, you have a new product, a new API, you run into the CORS error, and it's usually the allow origin error. You go search Stack Overflow or something for how do I get past this error? Very common, you just copy and paste an error. And one of the first things that comes up, one of the most common responses in the search engines is to just, okay, for something like Node.js Express, To install this little thing called Cores, the very first example is to just allow everything. If you do that, you automatically get past the error. You probably forget about it, and the thing makes it all the way into production, and these protections are never put back in place. So if you're running into this issue because of a security scanner or a security audit of some sort, this is likely the root cause, and understanding this root cause could help you understand how to prevent it in the future. It can help to show things in a couple different ways. So here's something I cooked up in order to show one of the common misuses of a site that Cores can help you with. Let's assume everything in the blue server is something that is protected and expected, and everything in the red server is something malicious. If you end up going to a malicious site, which is why the whole screen is red, it points to an API, such as one that you want to protect. If that API has the access control allow origin header as a wildcard, this star, which I show over the servers, then that server is going to allow that transaction to happen. So in the same scenario, the API server now has a access control allow origin of blue.com. So it's specifying that only blue.com is allowed to access this API or anything on the server. So when a user ends up going to the malicious site and it tries to make a call to the API on blue.com, it's blocked because the browser is not going to allow them to make that request from red.com. Here's a slightly different scenario where the roles are reversed. For whatever reason, you have content on red.com that is embedded in the site for blue.com. There's a number of reasons this could happen, whether the site is compromised or there's ways that were easy to inject content. A lot of older content management systems would allow this and didn't really check for it, and it's been abused heavily. So for whatever reason, your users are going to your site and there is a bad element within that site that is pointing them to a malicious server. If you don't set the cross-origin resource policy, then it's going to allow this. So if you set the cross-origin resource policy to same site, then when your user goes to your site and it reaches that content that's trying to go to the malicious site, it's not going to get there. It's going to be blocked at the browser based on your header that you set for the cross-origin resource policy. This is what you want. Here's a solution to the same framework that we did the Stack Overflow issue with. But in this resolution, by applying this library called Helmet instead of the other one called Cores, this one will automatically apply a lot of security configurations for you to be best standards, and it will get you past most of the basic things. It does include Cores. It goes beyond that a little bit, and I would recommend starting with this if you have an Express.js application, and it will save you some headaches in the future and plug up a lot of common holes that you may have created. On behalf of APIsec University, I'd like to thank you for joining us on this video. If there's another topic that you'd like to see, let us know in our Discord forums. I hope this has helped somebody plug up some security holes or have a better understanding of Cores in general. See you online.
Hi, I'm Anthony Aragues, and in this video, we're going to be talking about error disclosure, or you can also think about it as error handling with a security mindset. An error disclosure is when you have too much information in your error messages that are sent to a user's machine. It doesn't necessarily have to show up in a UI, but anything that's sent to a browser that a malicious actor can take and use to better understand what your system is in order to attack it is going to be called an error disclosure. Now, handling errors is necessary as a developer, and you want to intentionally error and error out actually pretty often and early so that things that are done maliciously don't work. But when you do that error, you want to make sure that you're not giving away information that's going to make it easier to attack your system. This means that you're going to want to have separate error messages for your developers to debug what's going on with the system than you're going to send to your customers. Here's a good example of a bad error message. From a user interface perspective, we have a bad error message in that it gives away too much information. If you tell somebody that there's an invalid email address when they are typing in emails, then they know that when they get the right email address, they're going to get a different error. They can enumerate the users or the email addresses that are allowed. This is a little different than what I'm talking about with error disclosure. This is actually going to be more commonly seen inside of your JavaScript console for your browser, or if you're attacking from a development standpoint, like using Postman or just your own little Node.js scripts, then the error below is what is going to be seen by somebody who's consuming the API. Now, interesting enough is these actually both came from the same interface. So one is the interface of the UI. I put in some SQL injection code, and it's just going to never send it back to the API. So they did some decent protection here, making sure that there's only a valid email address that's going to get sent to the API from a UI. But if I'm writing something to the API, I don't have to respect anything that the UI said. When you're coding for the API, you need to keep in mind people could bypass the UI. Not everybody's going to use that UI, especially if they're going to be attacking your business logic or trying to get at your data. They're going to go directly to the API. And in this case, it's not doing the same thing. It's not nearly as good about handling the SQL injection information. No, it didn't allow it to go through, but what it returned starts giving me information as to building a picture of what's behind the interface. And in this case, it told me that it's at least running Spring Framework, which means that it's running Java, and I can start to understand the code stack and probably some things that are associated with that, because we know that certain ecosystems have common components. And this is the type of thing that you would not want to display to somebody as an error message, because this isn't going to help any legitimate users. This is only going to help somebody who's thinking about it maliciously and trying to attack your system. Well, it's good to understand how this typically happens. It's actually pretty simple. A common development practice is to do try and catch blocks. In a try and catch block, you can catch the error and print it out. And I've got two examples here, very common ones. So in Python, you've got a try except, and in Node.js, you have the try catch. In both cases, it's very common to just print the error out or return the error. And even if you don't explicitly do the try except and then send it back, a lot of systems will do this by default. If you have an uncaught error, it will by default take the exception and send it back. So at least when you are intentionally doing it like this, you have more control, where you don't have to print it out. You don't have to send it back to the user. You could log it instead. And that is probably a better option, just so that it doesn't go back to the users. So try catch block, good thing to do, gives you control over what succeeds and what doesn't, and catches a lot of things that are unexpected, but probably not a good idea to send the exception error back to whoever's consuming the API, because it's going to help more than just your development people trying to debug it. So as an example of why it's not a good idea to put your technology information in your error messages, here we have a CVE specifically for that Spring framework that we found earlier. This is the kind of thing that a malicious person is going to do. Once they understand your tech stack, they're going to go look for common vulnerabilities for that tech stack. And then also, like I said before, trying to build out what other technologies are probably in that ecosystem, and then look for the vulnerabilities within those. And that brings us to the general concept of everything that you're doing. You want to try to think of how can it be used maliciously. So here's another live example that I grabbed just using my own little framework with Node.js. It's an example of a generic error message. So this is directly against the API. I tried doing the same SQL injection code for Postgres, and it comes back and just says, something's wrong. You might want to check the email ID. It'll do this no matter what I put in, and that's a good thing. And so this was for a forgot password, and it's not telling me if it was in the database, not in the database. It just hey, there's an error. If I was attacking this site, this isn't going to help me at all. And so this is more like the example of what you want to achieve. Something a little more fun and maybe not as applicable to an API is the brand approach. I've been seeing this a little more in the past few years, and I really enjoy it. This is GitHub's 404 error. Something to note is that GitHub will give you this error even if the page exists, but you're not allowed access to it, which I like, because if you don't have access to it, you don't need to know if it exists or not. So there's no reason for them to give you that information. They are treating it from a security mindset that if you don't need to know, they're just going to tell you it doesn't exist. But they do it with some style. You have the Octocat with the Star Wars theme. It's pretty fun. So as a quick summary, some things that you definitely want to do is you want to error early. That's going to keep malicious attacks from progressing too far, because it's going to hit something early on, fail, send an error, hopefully a generic error, that is going to keep them from getting any deeper or understanding the system better. You want to make sure that you include useful information for your developers and your support team, but that information should remain not visible to your customers. You might end up with an ID that ties them together, and that's fine. What you definitely do not want to do is bypass error. If you have a try-catch block with an exception, you generally will want to stop on that exception unless it's a known one. And anything else, you should stop execution. You don't want to expose development information to your customers. It doesn't help them. It helps people who are attacking your system. Hopefully you found some useful information here, maybe some things to think about as you're developing or understanding how to correct something that already exists. There's a lot of opportunities for exceptions to make it through the cracks whenever they're found. Hopefully these guidelines help you a little bit on not providing too much information for attackers. We're going to continue with the security series. We've got a number of other videos planned, and I look forward to bringing those to you. See you online.
Hi, I'm Anthony Ottawes, the head of APIsec Labs. In this video, we'll be talking about server information leaks. This is part of our larger series on server configuration security. A server information leak is anything that advertises your technology stack to random individuals online or your customers. It will do this through headers sent to any client that makes a request to the API or anything else that goes to the server. Sometimes this can also come from appliances or caching or your cloud provider, anything that sends headers. And these headers are going to be beneficial for somebody to attack you by understanding what technology stack you are on. So here's an example we can look at together. I have Chrome opened up with DevTools in the bottom half. And in DevTools, I'm in Network and then Headers, because Headers is mostly what we're going to be looking at. And with Network opened up, you can see all of the different requests when you go to a web page. When you go to a web page, it will do separate queries for its data, all of its API calls, its images, and all that kind of stuff. So you can start browsing through these, and then you can see where it went, what it sent, what kind of response headers it got. And these ones look like it's going to Google Ads. I don't know why it says Server Cafe, but these server response headers are what we're going to be looking at a lot, and especially ones that point to a technology that we can understand. You're not going to see a lot of really interesting ones on things that are hit so often that they have to be cached. Although I'm not familiar with what this is, I'm going to take this and I'm going to look it up. So we'll say web server. Oh, there you go. It's a Google web server. All right, so this is exactly what an attacking person is going to do. They're going to find clues in these headers, and they're going to go look them up and see if it's going to get them any closer to attacking the site. I find that I get more interesting things if I have an account somewhere. Go ahead and sign in. Now that I'm logged in, we're going to find some things that are less cacheable. They have to go to server, they have to go through an API, And that's more the kind of stuff I'm looking for. Now here I start to see different things. Like here's a interesting server I've never heard of called UVcorn. I did look this up before recording the video just to show you how this process would go. Go ahead and look it up here. And we find out quickly, this is an open source Python web server. So now I have something that I have the source code for. If I'm really savvy, I might find my own issues inside the source code, or I might just find things inside the source code that I can exploit, even though they aren't security issues of themselves. The better that you understand the variables, the parameters, the schema of something, the more successfully you can attack it. You have the source code. That's not that significant on its own. But then now that I know something specific about the server, I'm going to look up the CVE. So I'll say CVE and we'll get a list of CVEs. So if you're not familiar with CVEs, they are known vulnerabilities. So we can use that server tag to not only find the source code, but now I'm looking up specific vulnerabilities for that server. And the more unique that server is, it's not like a IIS or even Express.js, which definitely has its own vulnerabilities. The more unique it is, the more interesting it is to try to attack, because it's not trafficked as much, it's not known as much and given as much attention. Being able to find CVEs on something that is fairly significant, and you can expect people to automatically pick up whatever they can learn from the known vulnerabilities and try to apply it to your site that gives off that server tag that says it's running that. Just to illustrate it as a slide. So we went from what we had in DevTools. We had the server tag, which doesn't do your customers any good. There's no reason they need to know what server it's on. And they're probably not opening up DevTools anyways. From that, we were able to get source code and known vulnerabilities. Without walking through the entire process, I have found many other ones. Here's one with Nginx. Now, Nginx has 168 known vulnerabilities. So it's a little more, there's more options there to try, and probably less likely that individual options are going to work, but there's a lot of stuff there to mess around with. Nginx is a much more popular server. It's used even as a proxy or a cache. That is not as big of a finding as the one that we found before that was a more obscure Python server. But these exist everywhere. You're going to find that people don't protect this, and web servers will often just do this by default. They're going to advertise not only what server they are, but they're going to sometimes tell you what version, and that gets even more dangerous. So in the format of a quick checklist guide, when you are looking to analyze your headers for server information leaks, you want to use a client that is going to access your API. If you have a user interface that accesses the API and everything can be done like I showed in Chrome, that's fine. Or you can use something like Node.js, its natural ability to fetch API calls and call different methods. If you have that skill set, that's great. Or something like Postman will work as well. Anything that's going to show the headers, and almost everything will if you know where to look. And one of the key things is making sure that you get past the things that are cached. So a lot of these caching engines, they might also show up as showing their technology header, but it's not nearly as significant. What's going to be more significant is when an attacker knows that they've reached a server. They're no longer in cache land and have to break out of there somehow. They're going to want to get into directly talking to a server, usually through an API, want to know that their responses are actually getting processed on the server. It's actually hitting SQL, it's hitting data stores and returning a response. Now they've got something that's worth trying to fuzz and inject and see what they can get back. So the headers that are going to let them know that are the server, anything that says powered by, or anything that says version. Any of these type of headers are going to be something you simply want to remove. The way to deal with this is going to be different per web server. So I looked up a few. Like I said, I've never heard of this UV-corn. Maybe that's just me being out of the loop on some recent stuff. I looked up how to remove the header for it, and it has a regular option on how to do it. Just when you start it up, it has a server header option. I think every server I've ever seen that has these headers has a way to turn them off very easily, because it's not uncommon for people to want to remove this. This has been an issue for a long time. Nginx, the other example I showed, has a line that you put in its conf file just for turning off server tokens. In Express or Node.js, you can either run Helmet, which handles a lot of basic stuff for you, or you can specifically remove headers from your requests with the remove header function. I know that IIS and other popular web servers are going to be different. All of them are pretty easy to look up. There's nothing I tried looking up that was difficult to find. Just type in your web server that you're trying to remove the powered by header, and it's going to lead you in the right direction. On behalf of APIsec Labs and APIsec University, thank you for joining us on this video, and I'll see you in the next one. Hi, I'm Anthony Aragues, head of APIsec Labs. And in this video, we're going to be talking about cookie security and how to keep your customers safe from having their data harvested through cookies. Cookies are storing data on a customer's computer, and secure cookies are ones that are created that don't restrict the access to anybody who might want to read that data. When a cookie is created, it has certain security settings that can be created, such as the secure option, the HTTP only option, and then restricting what sites are allowed to read the cookie. Here's an example I've opened up where I've logged in. I found some requests that have cookies that are sending the cookies. There are some that are sending some back, but I wanted to show when you log in and it's keeping information on your machine, how much information that is. So here I've got a cookie that is sent to the server from my machine, and there's quite a bit here. Something to keep in mind is the cookie is pretty cumulative. It's going to keep as much information there as is sent from the server, and the server can add new key value pairs to that cookie, and it's just going to add on, and then there's time to live and a couple other factors. But the reason I want to show how much information is here is to show how easy it can be to access this, and that you want to protect it from being accessed by anybody that is going to use it maliciously. Here you can see I've taken that data, I posted it in, and I started to parse it. Now this stuff is stored in key value pairs, and so one of the easiest ways to start understanding it is to parse it by its delimiters, which is a semicolon, and you can start to see these key value pairs take place where you have a key equals and then a value. Some of these are just stored as Booleans or things that are easy to recognize, like a number. Then you've got these unique identifiers. There's some things in here that look like they're probably base64 encoded. Base64 encoding is fairly easy to decode if it's got no salt on it. And salt is an extra password that you put in to encrypt with it and makes it a little more difficult to decrypt it or decode it. It's different encryption. A lot of these ones with the equals might be base64 encoded. The reason I want to show this is because it's fairly easy to grab this information, parse it out, understand what different things there are. Here I've got a delimiter under delimiter. So we've got the key value pair that's already broken out, but then within it, you can see that I've got some pipe delimited stuff. And under that, I've got a session number. So a session number might be something that is valuable for someone to try to put in their cookie, have it send to the server, and then see if that works in order to get them past some checks. Here's another example of a cookie that is set, as well as how the cookie is set from the response header. So here we have the set cookie, and you can see it's got the session ID inside of it. And then it has these tags, which are going to be very important. We're going to discuss is the secure and the HTTP only. So these are some of the most important ones to do. It is possible to also define the location that is allowed to request the cookie, such as in the path. But secure and HTTP only are the main things that we want to look for. So this is saying set cookie, and this information is going to get appended to the cookie that is stored for this site. And it's going to send that back on the next time I come in. And that's how it's going to recognize me without requiring a login again. So cookie data initially will come from a server and be put onto a client's machine through the response header set cookie. And then when you go back to a site or something requests it, the cookie data is going to be sent back through a response header called cookie. Cookie data is pretty easy to access on a machine, and you can go through and analyze it and pick it apart and try to decide things from it. And for that reason, I both encourage people to not put anything into a cookie that you don't need to be there, and to also look at the cookies that you do have and try to make sense on if they belong there or not. So when you're looking at the cookie data, you're first going to break it into its fields by delimiter, and then try to find things that you think are interesting, things that say session or user ID or role, anything that you might want to set or somebody is going to have an incentive to try to alter or feed in a different value. You can also sort the different fields by their data type. Your unique IDs are only going to be useful as unique IDs. So you're not going to guess these easily. You're going to need another unique ID to try to plug into this value, or take the one that you see and plug it in somewhere else and see what you can get from that. But you're not likely to brute force unique IDs. You're going to have to keep lists of them to manipulate them at all. Numeric IDs, on the other hand, you can generally try to increase or decrease and see if you get different results. Booleans, obviously, there's only a couple values that you can use for Booleans, so it doesn't hurt to try changing them. And when I say try changing them, you can actually edit the cookie and then go back to the same website, and it's going to send that new cookie value to the website, and you're going to be able to see if you get a different response based on your change. So it's the same as changing field data when you're sending to an API endpoint, but in this case, you're changing the data on your machine. Too often, it's just accepted as this is only data that has been sent from the server, so nobody's messed with it. So you might actually be more successful in messing with cookie data than with API endpoint data. It should be treated the same. It still should be untrusted input. So for that reason, it's good to try to mess with it in these ways. Next on the list, we've got encoded data. And what I mean on this is generally the base64 encoded data. Sometimes it's URL encoded, but you can URL decode or base64 decode, and then you're going to try values based on what you find, and then re-encode it based on what you find, based on whatever it was encoded with. You might change a value, URL encode it, or you might do a base64 decode and see that, oh, this is a JSON string. Let me change some of these values, and then base64 encode it back and put it in the cookie. These are the cookie problems we're solving for. Cookie forging is the previous thing that I was showing, where you can take the data from the cookie, parse it all out, decide what to change, you change something, and send it back to the server and see what response you get. If you're able to access something that you weren't intended to, or impersonate a user or something of that sort, then the server is trusting the cookie data, and they should be treating it as just like they would user input data that's going to get exploited. Worth mentioning here that that's how all headers should be treated, because attackers can use any header, put in any value for any header, and those all need to be treated as untrusted. The next one is data harvesting from a different site. If you have the HTTP only flag on your cookie, it's going to keep the cookie from being read from JavaScript. It's still going to go in these request and response headers that I was showing in the examples, but it's going to keep somebody from being able to write JavaScript, harvest the cookies that way. And that is the most likely way that somebody's going to be able to easily harvest the cookies without being in the middle of your transaction. Data harvesting through cross-site scripting requires a separate vulnerability where you actually have a cross-site scripting issue. Somebody's able to use that cross-site scripting vulnerability to send a customer a link that's going to include JavaScript that then harvests the cookie, like I explained in number 2, and sends it off to them. So this one is definitely feasible and happens, but not if you set the HTTP only flag on your cookie. Unless you absolutely have to read your cookie through JavaScript for whatever reason, then you're going to set the HTTP only flag on your cookie, and JavaScript's not going to be able to pick it up out of customer browsers. And the last one is data harvesting in transit. And this is going to be the secure flag of the cookie that's going to help prevent it. It's just going to help. It's going to encrypt the cookie on its transport so that something in the middle is not going to be able to read it in plain text. The solutions to cookie security problems are going to start with treating cookies as untrusted user data. Once you have this mindset, a lot of the other things are going to fall into place. You want to keep in mind that the data that is sent from cookies can be manipulated. It's going to be treated as input on your server. And even though it's often not used as part of your business logic, you need to take a look that it is scrubbed for valid values when it is come in so that it can't be used to manipulate a user's access or do something more catastrophic on your server. Once you start treating it as untrusted user data, you're probably going to also be more restrictive about what you're going to put into cookies. If something can be used to manipulate someone's access or even the state of a process, you're probably not going to want to put it inside of a cookie. You're going to try to find a different solution for that and only use cookies as something that's going to keep track of your session or something that is absolutely required for your state management if you have it. And then analyze your cookies from an offensive mindset. Look at the cookies that are actually showing up in your browser from your application or from your API and parse them out, see what's easy to make sense of. Does it lend any clues as to the internal architecture of your system? Are you doing things like storing table names in there or something dynamic that somebody thought was a clever solution to a back-end problem that maybe you don't want to expose if you know now that people can easily go and look at it. So just take that offensive mindset, look at your cookies, see if there's anything there that you can then apply rule number 2 and remove that and move it to somewhere else. And then lastly, and probably most importantly, when it comes to the basics of doing cookies, you want to make sure that you've got timeout on your cookies, set something reasonable based on your policy, that you have the HTTP only flag that's going to keep JavaScript on different sites from reading the cookies. Remember, this JavaScript can be not only on your site, but on other people's sites. And even if your cookie is only for your site and you allow JavaScript to read it, then now a cross-site scripting JavaScript can read it as well and then send it off to somewhere else. So don't allow JavaScript to read your cookie if you don't have to. And then lastly, make sure that you have the secure flag set on your cookie so that it can't be read in transit or nobody in the middle can read that cookie as it's being transmitted. Thanks for joining us in this video. I hope you got something useful out of it. If you have any questions, feel free to ask us on Discord. We're going to be continuing with this series on secure server configuration, so I'll see you in the next one. Hi, I'm Anthony Ottawis for APIsec University, and in this video, we'll be talking about path traversal vulnerabilities. Path traversal vulnerability is anything that allows an attacker or user to be able to access files and directories that weren't intended to be served up by the API or web server. This can include things like direct file access, either inside or outside of the web root, or access to things that weren't in the web root at all, but somebody was able to get it through dynamic file includes or something similar. So we'll be going over various ways that can be done, whether it's through missing server configuration or a lack of defensive coding, or even vulnerabilities in your spec. So here's an example of a traversal vulnerability that I hope doesn't exist in the wild anymore, but it definitely would have 10 or so years ago, this blatantly because it was easy to do. There's lots of different ways that you can create traversal vulnerabilities, especially in server configs, but a lot of those have been tightened by default. but you can still mess it up when it comes to developing. If you develop something that allows a input to come in and directly be used as a dynamic file include of some sort, or a file path that you're going to then return, you're going to have a traversal vulnerability, and nothing's really going to stop you from doing that besides cleaning up your own code or thinking more defensively in doing that. So here is an example of a cookie. Remember, cookies can be easily crafted. And there's a number of ways that we can do these traversals, whether it's a ... to go to a parent directory, and you do that as many times as you need to in order to find the file that you're trying to get to. Etsy password is just a great example. If somebody can get a hold of it, then that's a very severe vulnerability. And then you can see in the PHP source code here where somebody thought, oh, well, if I just keep templates as a variable, I don't need to program each one. I don't need to list them or anything. So let me just include template. And since their assumption here was probably that because a template is a cookie and I send the cookies back to the client machine, then that's just a convenient way for me to store what template they're going to use. And then I dynamically include that as a variable name in my code, not realizing that if somebody opens that up and they see something says template, and let's say it says default.php or something like that, then they're immediately going to see that that is a traversal vulnerability, and they can then exploit that by trying different paths. Something that I don't think we emphasize enough is how important the spec can be to security. So here's an example where a data type of string is definitely going to be used against you on a number of different things, no matter what you're doing with the code. Strings that do these directory traversals probably should never have even been submitted back to your API server. It should have been caught by the gateway or the WAF. But when your definition for the data that's allowed to come in for different variables is loose enough to just be strings, then that's what it's going to allow. It doesn't know that it needs to filter these. It doesn't know that they're bad. So that's going to leave you to have to try to only define everything on the API, which is fine to list things in the API that are correct. But it's even better is if you can define your allowed parameters in such a way that it's filtered at your gateway or your web application firewall. I ran a directory traversal tool against Crappy, and it did 1,026, I think, different attempts at just the public paths that it could see. And all of these are going to register as strings. But you can see that if these were defined as a string for, say, someone's name or address or even a user agent, then they shouldn't have been allowed through. We can look at these intuitively and know these aren't valid as the parameters for a lot of the things that are needed for an API as variables coming in, not even from a cookie. The better that you can tighten what's allowed early on by putting it in your spec that's used by your gateway or your web application firewall, a lot of this stuff never gets through. It's not even going to make it to your API server to decide if it's okay or not. But then obviously when it does get to your API server, if you can list out what is allowed rather than trying to filter all these different ways that it can be encoded, because that's one of the things I want to show is how many ways it can be encoded. URL encoded, it can use the ASCII encoding, Unicode encoding, anything that it thinks is going to be happening on the server end to filter. Some servers will just try to filter ... and you can put it twice or intersperse them so that the removal of any ... is going to leave a ... as the next iteration. So all of these attempts are actually all the attempts to bypass the common filters. And it's just not a game you want to play. You don't want to play the filtering game. You want to try to define what is valid and good for your application and only accept that. The problems that create a path traversal vulnerability are listed here. We have our input data validation, which is the logic level of what to validate. that is allowed for different parameters before you use them. We have a server configuration, and this is the one that is pretty tight in more recent versions of web servers. If you're running an older web server, it might not have these as default, but hopefully you've plugged it up since then. If you ever find a server configuration that allows directory listing, you need to cut that off. You don't need to give people directory listings. There's no benefit in it. I still run across it, especially on Apache web servers, but you want to cut those out. And also allowed include file paths. So when you have your API server, or typically a web server that's serving an API, there's the web root, and then there's everything underneath the web root. And there's usually a server configuration checkbox that says to only allow inclusions or files that are under that web root. Never allow anything outside of that web root or above that web root to be used. And that will help somewhat. They still might be able to get files you forgot to remove from the web root, and we'll talk about that in a bit, but it will at least keep them from going above the web root to something like a system directory. And then, like we mentioned before, the loose definition of a string for your parameters that are allowed that are in your API spec is also contributing to the problem. And something as simple as even giving it a max length can go a long ways to thwarting a lot of the payload attempts that I was showing with the past traversal. To check on how prevalent a vulnerability is, you can always go to look at the CVE details. And the CVEs are known vulnerabilities, and they're often categorized in the same way that we discuss vulnerabilities that are found and that we test for. You can also find things by similar names in the CVE databases. So when I just look for this category, there are thousands that are there. Here you can see when I sort to try to get the latest ID first, that these are still happening, right? We still have path traversal vulnerabilities that are found in applications today. AutoGPT, that's a really recent one. And a lot of these are going to be found in places you didn't think of. You have a function that needs to have a file name. It needs to grab something dynamically off of disk. Let's say a customer or a user of your application has a thing where they're supposed to upload a file, you process it, and then they download a file. You allow a variable to say, what file am I going to get? That's going to be something that somebody's definitely going to try to exploit for a directory or path traversal vulnerability to see if they can dynamically get something else, right? It doesn't have to be something like the PHP example where I showed it displays whatever file that it's trying to access, but instead it can also try to retrieve a file whenever that's what the logic is supposed to do. If it's supposed to retrieve a file and send it to you, like some of the examples here, then you can try to get it to send you a different file. These are definitely still occurring. These scores are low in how they're exploited to get different things, but they definitely get higher. And you could see that the ones that we had with higher severity were some of the older ones because people had figured out how to connect them together with other vulnerabilities. Unless they can actually directly access something like your Etsy password, then they will often keep the severity low until they can connect it with something else that allows that level of access. But yeah, they're definitely still occurring. They're still out there. People need to take it seriously as something that is both easy to make a mistake on in the coding and easy to exploit if it's there. Let's go through the solutions real quick. So we're going to scrub the input data. It's worth repeating in every video. Disable your server directory listings. That's a web server configuration. Also in a web server configuration is the setting to allow something to access anything above the web root. That is commonly done by default, but it's still something we're checking. And in addition to that, you want to make sure that nothing at the web root or lower is something you don't want anybody to access. If nobody's should be able to access it, just don't allow it below the web root. That includes your hidden file systems such as your .git or your repo type things that might end up getting copied in because they just went along with it. It would also include things that might be a README or something that has sensitive information in it, environment configs for other environments. You want to just get those out of the web root. Don't ever assume that you're filtering so well that they can never be accessed. To go a step further than that, you could put your web root on a completely separate drive. That way, if they were able to somehow traverse directories up, it's not going to get them anywhere because they would need to change drives in order to get to that location. You definitely want to remove variables from paths in your source code if you are able to. Like the example I mentioned before, if you have files and you're supposed to serve those files, you're going to have some dynamic stuff there, but still probably the best pattern is to have an ID. The ID is then used to find the path, and that is the path that you're going to retrieve for the file for your API response. Anytime that you're going to take a variable and use it for a dynamic thing to access the file system at all, there's the danger there for these vulnerabilities. So just try to avoid it. And lastly, if you run across something that is unexpected, you should error. It's better to have an error and log that error somewhere to research what's going on than to be so permissive that you're allowing things to get through that should not have gotten through. And then you get to a layer that you didn't think anybody would be able to access because they were able to create exceptions down a path until they got to something that was fairly insecure. So as a quick review, path traversal vulnerabilities can be really severe. They shouldn't occur that often, but you should definitely look at anything that dynamically includes things from the file system, anything that dynamically accesses the file system in your code. They should be easy to find by those patterns. The reason I say that it can be severe is if you look at the examples of the type of things that it could access, especially at common paths. People know where etc password is. They know where your host's file is. If you're on a Windows server, they know where your log files are going to be. So all they have to do is try all the various encoding and escape bypasses in order to try to access those locations. Obviously, they share some common solutions as the other vulnerabilities that we've been talking about. One of your best ways that you're going to be able to know if you have these issues and prevent them is to both do your testing like tools that will do the path traversal or directory traversal attempts against all the different inputs that go into the request and response process, and then a static analysis. So there's no substitute for static analysis of your code, finding these locations that may be dynamically accessing the file system. Thanks for joining me in this video. I hope you got something out of it. Happy to discuss more on Discord, and I'll see you in the next one. Hi, I'm Anthony Aragues, and this is the rate limiting course for the Secure Server Configuration series. Rate limiting is much more than a couple of things that you configure on your server and you're done. It can incorporate your business workflow, your needs, your budget, a number of other things, and even just known limitations of your application. You do want to set your rate limit headers that are going to be respected by some browsers, and the HTTP status to 429, which is the accepted one for too many requests. But you also need to configure things based on individual endpoints, how frequently they should happen, and for what scope. Rate limiting is more significant than you might think. The OWASP Foundation came out with their new API top 10 list for 2023, and number 4 is unrestricted resource consumption. Now, this is exactly like the broad concept that we're talking about today, not just a couple of headers. If you care about the OWASP top 10 and it's part of your security framework, then that could be just enough of a good reason. But my primary reason is for the service availability. I want to make sure that when I write an API, that the primary use that it needs to serve is serving the people that are supposed to receive it. And it's not overwhelmed by things like botnets and scanning or even just sloppy use. So the more limits I can put in there in order to keep things on that path of what I'm expecting it to be able to provide, the more likely it's going to be able to provide that. There are a few security considerations or security scenarios where a overwhelming of resources in one area will allow a vulnerability to show up in another, but these are fairly rare compared to just general rate limit scenarios. And finally, we have the budget consideration. When you've got everything hosted in a cloud, for instance, and it is priced per processing hour or bandwidth or concurrent users, it's simply going to cost you more money the further into the network that you allow that connection to go. There's a lot of different layers that you can enable resource limiting to your needs at that specific layer. The earlier that you filter out a process that doesn't belong going further into your network, the more headache you're going to save yourself, the more budget you're going to save yourself, and the more that those lower layers can handle. For instance, if you are able to set something in a load balancer that limits your general number of connections or requests per session, then that's going to keep things from getting to the much lower layers of things like logic, where you programmatically debounce whatever a user is doing. Considering each layer for what's appropriate to limit resources at that point and using them in these layers is going to be your best strategy for tackling the problem overall. So for this one, we actually have something fun to play with. If you have done the Hacking APIs course, then you're already familiar with Crappy. But Crappy is an API that's intentionally designed with some vulnerabilities and released by the OWASP Foundation. You can download and host it yourself, or we've got a hosted version that you can play with. Again, that's over in the Hacking APIs course. It has a rate limiting issue built into it, where if you use the contact mechanic feature, you can overwhelm the database with inserts so that the reads are slowed down or completely blocked on reoccurring, depending on how hurt that database instance is at that time. The way that you can prevent this kind of stuff is just by thinking per endpoint, how often does this make sense to happen? And how would I define how often that makes sense? When it comes to something like contact mechanic, if you can put authentication in front of this, that's going to make a big difference. And then beyond that, now that you have authentication, how often should somebody be hitting this contact mechanic form, say within a day or an hour? I wouldn't think it should be very often. And if you reduce how often they can do it within a time frame, it's going to set that limitation to something that still works for your business, but saves your resource consumption and sometimes a security issue. And that brings us to our first scenario for rate limiting, which is the application layer denial of service. Now, I say application layer here after just talking about a whole bunch of layers, because this is the most common one, or the core one we get to. If you are able to filter a bunch of things at higher levels or earlier in the network, such as the load balancer, then it won't get to the application layer. We don't have to be talking about this. But when we're talking about an API, we can get down to, look, the lowest level of issue that we're talking about is the application layer that we're worried about, and all the other ones are kind of leading up to it or in support of it. Something like a botnet is going to typically send unauthenticated bursts to an endpoint. So if you require authentication on an endpoint, it cuts most of that out. If they do have credentials, then it's going to be probably very few users that are valid. And so then you could use that user to monitor and limit the frequency of the endpoint calls. Those are the best case scenarios when it comes to, being able to handle this very quickly. Authentication is going to cut out most of the noise. If you can't put authentication in front of endpoint, then you can do a couple of things. One is try to do some kind of a CAPTCHA and make sure that it gets through to the API layer. It's not just a presentation layer or CAPTCHA somewhere. That will make a difference. You can also do things like look at sessions or the client signature. Client signature goes beyond an IP. It's going to include everything that you can see that's coming through the request headers that you can hash, and you can do some filtering that way to at least make sure individual clients can't continually spam the endpoint with requests. So the impatient user is both a funny and very realistic scenario. This is the person that typed in a bunch of stuff in a form, they hit submit, and then they can't wait half a second before they hit another submit. And then after that, they might just click it 15 more times, thinking that they're going to get a faster response the harder they press their mouse button. Never mind any of that logic. That is actually one of the easier things to deal with because it's not anything malicious. It's just someone impatient, and we can handle that. You can handle it with making sure they get an immediate response that says, hey, you got the request. You don't stall out on it. Obviously, when we talk about an impatient user, it's probably not the direct API call, but the API that responds to the UI. Giving a immediate response that says, hey, we got it and we're processing it, that's going to help, even if it's not something that has shown new results they're expecting to see. If you get X number of requests within a few seconds, you probably want to just debounce that, which is to literally mean keep the key from something bouncing on the key and take the last value and process that one. I included this funny error message from Twitter that was an official thing. I ran across it myself. I laughed out loud. If you don't understand why it's funny, I'm not going to explain it. Now we can get to a security use case, which is brute forcing. If someone can brute force an answer to an endpoint, all they need is time and number of retries in order to find what's going to allow them in. But we've reduced it to a couple of realistic scenarios that are going to work. We're not talking about just being able to brute force a password with millions of combinations. We're talking about something that is much more manageable. A 4-digit PIN, for instance, say in a forgot password, you're sending a 4-digit PIN to an email or to a phone, know that it's going to take only 10,000 combinations to guess what that PIN is. And this isn't going to be authenticated because they're getting their PIN for their forgetting of a password. All they need to know is a username, and then they can start guessing the PIN combinations. If you are allowing 10,000 combinations within a short time frame, that's the time frame you're allowing them to get the new password or change the new password. They need to do that with a valid user, which is where user enumeration comes in. User enumeration is done by understanding that there's a difference in response or response time for a valid user versus an invalid user. So you can do this by just running a large list of emails. They just have to be valid emails or common usernames, and you look for a difference. If there's a consistent difference, say a very fast response time for the users that aren't found, that helps. And if you get a actual difference in text, like we found this user, but the password's wrong, you know exactly what you're dealing with. Some errors like that will really help you in hacking their API. So that's user enumeration. If you can find out all the users, then you can take those users or even just a few of them and then use the 4-digit PIN to take over that account. Definitely a combination that you want to avoid. And then finally, we've got scraping, which might not be a actual security issue, but might be a business issue that you want to avoid. I still put it in the brute force category. And this is where you might have thousands of pages and you are fine with somebody going interactively through those pages, but you've enabled this through an API. So somebody has decided to use that API to just get every page loaded into their own database and scrape your data away from your site and use it in some other means, and might be something that is a concern to your business. The methods for dealing with this are going to be for the PIN combination, make sure that you have a somewhat low limit. Maybe 6 times would be the upper limit of how many times you can guess the PIN, and try to limit that based on client signature, maybe even IP. That's not too big of a stretch to say, I don't care if you're all in the same cafe sharing the same IPv4. If you're all trying to guess your PIN at the same time, there's probably something fishy going on. Keep it something low. You might be able to use client signatures and such that we already discussed to help with that. And then when it comes to the user enumeration, just use the same exact error message. And if you can, use the same response time for the valid users versus the invalid users, and just let them know, hey, if this is a valid user, we will send you an email. And if they are a valid user, they'll get that email. If they're not a valid user, then they have no clue if it was valid or not. Our final scenario is based on budget. Maybe you bought some cheap hosting, or you are on a infinitely scaled cloud. Either way, you want to pay for your users using your service for what you intended it for, not for everybody overwhelming it with bogus queries or trying to brute force it. If you care about the cost of your services running, then that could be an incentive alone to look into all the different ways that you can weed out the invalid requests, the brute forcing requests, all of the spamming of your endpoints, down to just what you expect for the business and you budgeted for. Finally, I want to leave you with some technical tips in order to work with just a little bit of guidance based on some experience on handling this myself over the years in this same exact area. You don't want to use SQL operations in order to do your throttling. If something is expecting to happen, say, thousands of times per second, waiting for a SQL insert or a SQL read is just not going to be fast enough. I'm talking about your relational database type stuff. If you've got some fancy in-memory NoSQL or SQL operation that happens that doesn't ever hit the disk, that might be something different. But try not to use your traditional like Postgres or MySQL database to manage your throttling. It's going to have a limitation on its own. One of the reasons for that limitation is because of the disk operations. Like in many things, the more you can stay in memory, the faster you're going to be able to respond. So any disk operations that you can avoid, say, if you decided to have a file that does this kind of thing, I would avoid that as well. Even though disk operations don't have quite the same overhead, they're a little bit different than the SQL ones, I would still avoid the disk operations. I do recommend making sure that if you create a user signature, that you might do that with the IP, or at least take into consideration that the IP and user are not the same thing. If you see a user across multiple IPs at once, that could be interesting to look into. Or if you see an IP with multiple users, that could mean something different. That's going to be a little more common. Use cache where appropriate. I've done a number of solutions where I take the same exact query from the same user, etc., make that a key, and then the value is the response is the value, and I can serve that back much more rapidly than if I reach down further into the service and have to hit databases and such. And so I can set a different rate limit for cache responses than I can for something that's going to be process intensive and reach deeper into my application. So that could have an impact on your rate limiting, where you can open it up a little bit depending on if it makes sense for your business scenario. And you don't necessarily have to be super restrictive until it's going to take a lot of processing time and resources. And then finally, we've got the throttling solution, which is similar to the cache solution I mentioned. The reason I mentioned things like memcache is it's in memory by design, very lightweight, has a number of solutions out there, and there's lots of stuff that's progressed way beyond memcache, but they're kind of memcache based, where you can have a quick key like a client signature or IP plus user, then have a short time frame that is its TTL, and you can use that time to live as the actual throttle and look for if there's a block already recorded in your memcache to say chill out, or if you are allowing this request to go through. Just a couple of different ways. There's always multiple different ways to go on this stuff, which is more discussions that we can do in the APIsec University Discord. Welcome you to join there. Lots of people have joined there and have conversations about API security and building secure APIs in general.
And with that, thank you for joining me and hope to see you online soon.